I'm very proud to be able to address you today. As David said, I spent quite a bit of my career doing the same thing that you do, EDA, in its various flavors, let's say. And then a few years ago, while at IBM research, I somehow had an opportunity to do something else. And the talk today is about that path that took me from a life of an EDA researcher to the life of a researcher who works in a different area. And I'm hoping by this to show maybe the possibility that many of you may have in the future to apply the training that you have in other interesting areas. And I would like to apologize a priori. My wife is a singer, and on Saturday in Austin, she has a concert. And I promised my wife, because I love my wife, I hope many of you love your wives, I promised my wife that I will be at the concert on Saturday, which means I have to leave here immediately after my speech to take the train, to take the plane, to go back to Austin, to be in time to see my wife as she is singing. So my apologies. My email is on the slides. And if anyone would like information or has a question or a comment or a criticism or anything that you would like to say, I'm more than happy to get your email and to respond to your email, so please feel free to do that. So I will start with my first life, my VLSI life. You all know what chips are, and to me, when I look at chips, I see three distinct things that happen in those chips. Chips have logic. These are circuits that do some kind of computation. Chips have analog. These are circuits that are used to interface the chip with the outside world. I don't want to talk about analog too much because analog people are very strange to me. So we will not talk about them any further. I know. And then the third one is memory. Memory is the circuits that store information. And if you look at any picture of a modern chip, you will see that memory usually dominates. Most of the chip is made out of memory. So much of the progress in our chips over the last 50 years that we can say has been Moore's law, much of it has been about going faster and storing more. And they have to go together because the faster you go, the more data you need, the more storage you need, etc., etc. So the outcome of that is that memory is a very important part of chips, and designing memory is extremely important. However, it is difficult. It is difficult because with scaling, we are ending up with many, many problems. When we make transistors, the transistors aren't all the same. Just like if you go in your garden and you pick up some tomatoes, they will be different sizes, they will be different colors. Some of them may even be having a worm inside, and you really don't want to eat that tomato. So the problem here, of course, is that making chips is not like making tomato sauce. You cannot take all the tomatoes and put them in and make a chip. Every one has to work. This means you have to be very careful in your analysis, very careful in your design to make sure that you get a good result. What does that mean? That means that there are many, many papers and many PhD theses and many IEEE fellows and many best paper awards, many, many things about memory. And specifically, my group at IBM, when I was there, we did some memory work. We used to do memory design, memory analysis, and part of that work was making sure that memories have high yield, which you all understand to be something about variability and things like that. At the core of all of those techniques, at the bottom of the pyramid, if you like, of the analysis, is Monte Carlo, right? Because in the end, you have to evaluate some yield integral over some multidimensional space, blah, blah, blah. And the most convenient way to do that is Monte Carlo. So now we get to the accident. The accident happened because of how higher level management works. I do not want to criticize higher level managers, but I will. But what I notice about them, and for those of you who are not high-level managers, maybe just department heads or senior professors, it's the same thing. Once you have been doing management for a while, you stop being able to use GCC, you use Excel. You stop being able to use the Cadence layout editor, you use PowerPoint. So in a sense, your technical skills, let's say, become less and less. And when you are giving talks or when you are talking to people, let's say the low-level technical detail somehow is not there anymore. You can talk about it, you know some of the words, but you really are not doing it yourself. So my manager, sometime, was visiting the MD Anderson Cancer Research Center in Houston. This is one of the premier cancer research centers in America, a huge place, 50,000 people, campus as big as a university, blah, blah, blah. So he was there, and then somebody was giving some technical talk, and that person said, oh, Monte Carlo. And my boss says, hey, we do Monte Carlo, we know Monte Carlo, even though, of course, it's a completely different Monte Carlo. And out of that came the adventure that I'm describing. So now we shift from VLSI to my new life, cancer treatment. There are three major ways that you treat cancer. Surgery, you cut the tumor out. Chemotherapy, which is essentially poisoning the tumor. You are giving the person various kinds of poison to kill the tumor. And radiation. I will talk more about radiation in a little bit. There are some very interesting things happening recently on immunotherapy that you may have seen in the news. This is still a small part of the overall cancer treatment area, but it's promising very much, and it has many big data kind of aspects to it. And when you have a treatment, God forbid if you have cancer, you will have some mixture of those. You may have surgery with chemotherapy or chemotherapy with radiation or some combination of the two. It is usually not one only. The doctors like to shoot as many bullets as they can at the cancer, so they will use multiple methods. Specifically for radiation, the name of the game is to try to deposit energy into the place where the tumor is. Because what happens then is that energy disrupts the DNA. And when you disrupt the DNA, the cell isn't able to replicate itself anymore. And because it doesn't able to replicate itself, it dies. Now you have to remember that cancer cells metabolically are much more active than normal cells, so they want to double themselves much more quickly, so they are more sensitive to this kind of phenomena. So if you can put the energy in the right place, you can kill preferentially the tumor cells before the healthy cells are dead. There are two kinds of radiation. One is X-ray, which is the more common kind, cheaper kind also. And then there's proton radiation therapy. This is a little bit more expensive, a little bit more precise. It's like the difference between a flashlight and a laser beam. So a flashlight, you shine it at the tumor and you try to sort of make the tumor go away. With the laser beam, it's a much narrower beam, but you have to be much more precise. Unfortunately, the X-ray machine, which is the not so precise, is maybe $5 to $10 million. The proton machine is more like $150 million. So, you pay for what you get. This is the process that people go through for radiation therapy, and I know you cannot read this, but it has basically three major stages. The first stage, you find out where the tumor is in the body, and then you figure out where in the person's physique that tumor exists. In the second phase, the one that's labeled dose planning here, some doctor and some physicist figure out how do we get the energy to the place where the tumor is. And then in the third phase, the treatment phase, some nurse will put you on a machine and then irradiate you over 35 days, usually multiple fractions they call them, until hopefully the tumor goes away. In this world, in this process, And again, it's too much detail in this picture, but you will see that the middle part is the most difficult because the first part and the last part is mostly nurses. The middle part involves doctors, oncologists, as well as physicists, people who actually understand physics, because they are using essentially a particle accelerator to put the energy where they want. So you have people with a PhD in physics who are actually doing the treatment. So that translates to expensive. This is expensive time. In this process in the middle, the expensive process, there are two parts that are quite time-consuming. The first one is called dose planning. This is the one where they are trying to figure out what is the best beam to get to this tumor while maybe leaving some other part of the body safe. And then the other part is called dose calculation, which says, if I put this beam into this patient, where will the energy go? Will it go to the correct place in the patient? It turns out that a typical treatment, if there is some difficulty, perhaps maybe some tumor close to the heart, or a tumor in the head, where of course you want to try to avoid other parts of the brain, it can be quite difficult. You may do several iterations in that loop, meaning multiple days, even weeks of planning time. And of course, making this process slow means that the patient is waiting before the treatment happens. And of course, the patient has cancer, is maybe close to dying, so time is important. It is not something you want to ignore. So when people do this today, they use existing tools, Monte Carlo tools in fact, and those tools are quite slow. They are meant to be very general and very accurate, but they are relatively slow. So when you do this Monte Carlo, for each particle, approximately 30 milliseconds of computation. So you say, oh, if I want to make a 20 million particle beam, which is a number that gives you some good confidence in the statistical results that you get, it's about 5 core weeks. So 1 core, about 5 weeks time, a long time. And of course, since it's Monte Carlo, it's trivial to put a huge data center on it. And if you can put enough cores, you can bring it down to 1 hour if you want, of course. It's not hard to do that, but that's all commonly known. This 5 core week, when I saw that, I said, no. We can do better than this. We're engineers. When we simulate a full circuit, we don't simulate it at the device level. We are very clever about abstracting things so that we simulate each level at the appropriate level of granularity. So we did this. Me and a team of people from IBM, we left IBM and we started working on this topic. And we came up with a dose calculator, which is about 100 times faster than what people currently have. And don't be afraid, I'm not going to go into technical detail of how we implemented it, what the details of the inside, that's not the purpose of this talk. If you would like to know about that, send me an email, I'll let you know about it. But the purpose of this talk is more about the journey than about the destination. We did this, and we did this by applying techniques that you all know. Essentially the technique of abstraction, right? Realizing that it makes no sense. If you're doing something 20 million times, it makes no sense to do each of those things to the 15th decimal, right? You can be very clever about how to do that. And this has changed how people do this. So the results that we are getting from this code are changing people's perceptions about how Monte Carlo can be applied. And to them, Monte Carlo is the gold standard. Monte Carlo is the most accurate measurement they can make. So it's very important to them because it gives them accuracy while at the same time giving them speed. We did this without compromising on accuracy. So of course you could tell me, oh, you can go 100 times faster, but maybe you give up some accuracy. And of course Monte Carlo is known because it's accurate. And I'm not gonna go through this picture in great detail, but we do a very exhaustive comparison between what we do and between the other tools, and we are as accurate as anybody needs us to be. The other part that was very interesting to me when I entered this area, and again we used a lot of knowledge from EDA, is flexibility and ease of use. If you are writing a tool for somebody, and that tool is hard to use, the tool will not be used. Or the tool will be used very rarely. It is only if you can make the tool very easy to use, if you can make the tool have a very easy learning curve where you can do simple things very quickly, and if it needs to be complicated, maybe it requires more investment, but at least you see the return on that investment. Only then can people use those tools. The tools that existed require you to write C++ code to do the simulation. Now, we all know C++, or if you don't, then maybe you shouldn't be in this room, perhaps. Unless you're a senior manager, then it's okay, because you know Fortran. You know Fortran. The point is that, in order for you to do a simulation, if I require you to write C++ code to define the geometry, define what the particles are coming from, define what the properties of the particle, that's a lot of work. And a lot of work that maybe is not useful when you run from one time to the next. You cannot reuse that code very effectively. So one of the things that we did was we said, no, we will apply the same ideas we have from EDA. We will use simple file formats that everybody understands. We will use standards where possible, as opposed to inventing our own things. And we will then put these together and make a very simple set of demonstration codes that people can then use. And now, all of a sudden, students that are starting in radiotherapy can actually do a full Monte Carlo without having to learn some large piece of code and learn C++ and all this kind of stuff. This was another big lesson of applying EDA knowledge to this other area. This is some just cool picture to show you that we don't just simulate, obviously, nozzles and things like that. This is a case where a brain tumor, and it shows a comparison between our tool and between the standard tool in the area, which is called GANT4, which was written at CERN. So you can make, of course, patient cases and evaluate all of those things. So I wanted to show you the metamorphosis, what changed in my life between the time that I was at IBM and previously at Bell Labs, manager and things like this, to today. Before, I spent half of my time in meetings, and usually not very productive meetings. You go to a meeting, and some person has to say something, and some other person has to say something else, and then it just goes on, and then you ask yourself, what was the product of this meeting? And it's not always so easy to say. I was also a manager at IBM, and so I had boss duties. Oh, this person wants vacation, this person wants to travel to date, and this other person wants a new keyboard for his computer because blah, 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 whatever, the usual things. And then phone calls. Many phone calls from probably you, from professors who we were doing joint research with, phone calls and all that. And the only part that I had for technical work usually was maybe an hour in the morning where maybe I was able to do some coding or some experimenting or running something. Today, in my company, I spend more than 80% of my time coding. Yes, I'm the CEO, but I actually write code. I actually enjoy writing code. Most of the pictures that I showed you before were from pieces of code that I wrote. And then, of course, I come to meetings. I should put a sliver here for going to date and giving keynotes, but that's not important. So, now my time is almost entirely dedicated towards doing stuff that I personally enjoy. What have we done? The first thing we did when we formed the company is realize we're EDA engineers. We don't know anything about this area. We know some small things, but you have to find experts. And so we found a world-class advisory board. We went and found key people who knew what they were talking about, who were respected in their area. And surprisingly to me, very surprisingly, even though they don't know who I am, maybe they know a little bit about IBM research, or they have heard a little bit about what IEEE fellow means, I don't know. They said, okay, we will serve on your advisory board because you seem to be promising. So we got a world-class advisory board. We made relationships with the top hospitals. It's not hard to say, where are the top research institutions for this area? Mayo Clinic has a very good research program. St. Jude, Mass General, MD Anderson, etc. And then we opened dialogues with all the people who could buy our code. You know, if you want to build something and you want to make money off it in the company, you should know who the customer is. And you should start talking to the customer before you have a product, because they may have something to say about how they would like this product to be. So instead of sort of doing research for research's sake or writing code just because we enjoy writing code, we try to do it for the specific reason that, oh, we have a goal in mind, we have a customer in mind, he says he wants the following, let's go build that thing. And so we wrote the code. You know, that took a year and a half, but in fact, that's the boring part. I mean, we can go through the mathematics and the code and all that, but it's all straightforward, right? And we've now had it verified in several places. So several of the research hospitals have taken a look at it. One company that is negotiating with us to buy it had it evaluated at CERN, where all the physicists are. They said, we want to evaluate your code. I said, fine. They said, send it to CERN. And I said, oh, send it to CERN? But yeah, send it to CERN. We sent it to CERN. CERN looked at it. They said, sure, this code works. So, you know, it's not hard. And now we've closed our first major deal to license our code. So we made some small amount of money. And we already are in active negotiations with several other companies. And more recently, the Mayo Clinic decided to buy our code as well. So people who know what's going on, who are doing research in the area, who have a need for this kind of tool, are basically saying, this is good. Even though you come from a completely different area, even though your background has nothing to do with radiation or oncology or anything like that, you have a product that works. And so much so that, hey, we're willing to pay you money for it, which is extremely gratifying. So once you could ask me, what is the recipe? Besides having a job that is, besides having a boss who goes to MD Anderson and says Monte Carlo and by accident gets you involved, what is the recipe? How do you do this? I would say that the most important part is to be open and collaborative. Realize that even though you may be the top dog in your area, you have 15 best paper nominations and 14 best everything you want, best EDA articles, etc. You could be a fellow of it doesn't matter. You're going into a different area. You have to be open, you have to be collaborative, and most importantly, humble. You are going to talk to people who know more about this area than you ever will. You have to be convincing to them to tell them, I can help you. I can do something that will perhaps help you, and maybe convince them I'm smart enough to help you. I have some background that would be useful. You also have to have confidence. You cannot go and say, I don't know anything about oncology. I don't know anything about this. You have to say, I am an EDA engineer. I have lived in 50 years of exponential growth. No other field in engineering, humanity-wise, has ever had to do something as hard as we did. Every year and a half, we have to solve a problem twice as big as 2 years before. No other field had to do that. That should give you confidence. We are not idiots. We know what we're talking about. So with this confidence, you can go to somebody and say, my field has done good stuff. I have done good stuff in my field. I think I can help you. And a smart person maybe will say yes. And networking. So you guys are all networking here, but this is kind of like networking within the field. You have to figure out a way to not go to the EE conferences, but maybe go to the other kinds of conferences and find other kinds of people and network with them, because this way you improve the chances of doing something outside. I network when my wife sends me to her parties. My wife is a singer, so I go to her parties and I hear all kinds of things because I'm with singers, not with engineers. And finally, courage. It is very, very hard to leave a comfortable place where you're known, you're CEDA president, everybody knows who you are. You have papers, you have students, you have professors who are your friends, who, you have all of these relationships, and yet you have to say, somehow, I want more. This is not enough for me. I want more, and I want to show that I can be more than this. I can be more than an EDA engineer. I can take my EDA background and apply it somewhere where maybe not immediately it's obvious that I can apply it. But by doing that, you are helping yourself, you're helping your confidence, but I hope also helping others. I hope that by showing you this and sharing it with you, I give you an example, especially for the younger students who may be graduating soon and asking themselves, what should I do? There are many things you can do. And I hope that you will all have the courage to explore those alternatives. And I hope that those alternatives will bring you careers that are as satisfying as I'm finding mine to be. Thank you very much.
Thank you for this enlightening talk.
Thank you, Ahmed.
I have a question for you because I met people experiencing this, and I always ask the question, if you are living looking for more, what are you looking for? You left EDA, you left your job, you left your boss position to go coding C++. What were you looking for?
So, Ahmed, when I go to parties with my wife and somebody says, what are you working on? And I say, my last job at IBM, 14 nanometer SRAM FinFETs. Very, very important topic, right? I say, yes, we are working on, in fact, at the time I was working with Professor Asinov from Glasgow, and we were having a project on how to improve the planning and the execution for the 14 nanometer SRAM FinFETs. If I say that to somebody, maybe even some people in the room, so what I was looking for is I was looking to be able to tell my mother, Mom, this is what I'm doing. And my mom says, good boy, good boy. That's what I was looking for.
I personally have a question about we're having the other day a panel about funding. Mm-hmm. Because when you take this type of decision, and actually in the PFL we have few programs where we try to encourage students exactly when they're going to graduate to leave and do these type of things. Typically what we find is that in the US tends to be harsher, but also easier to get funding. But this applies to the area of EDA. So mm-hmm. How does it work in the area of biomedical? Because in the area of biomedical, you need plenty of money for doing these type of things. Some people will tell you, we don't wait to give you the data, we need to have some kind of cooperation. Yeah. If you're a tiny guy, like you say, that you go to another field that they don't even know you, how do you manage to convince them this?
Well, in all honesty, I cannot say that I have experienced all aspects of that, but I can say some comments. First, my observation, and I think probably everybody who knows maybe some friends in the medical area will tell you, funding in medical is quite a bit more plentiful, let's say, than in engineering. Their problems are not terminating with Moore's law, slowing down, etc. They continue to have problems. So that's the first part. That said, there are many more issues in medical. So I didn't mention it here, but liability is an extremely important topic which we as EDA engineers do not much think about. But if you are going to write software that perhaps matters to somebody in a life or death situation, you are liable, you are responsible. Your company could be sued if that person doesn't survive, right? So there are definitely a set of different issues there. So funding is one, the intellectual environment is quite different, and also the collaboration environment is quite different. Because of requirements in the United States as far as patient privacy and stuff like that, it is actually harder to share data effectively. You can share some things, but not enough. And like some of the things that we talk about in terms of big data and stuff, it's actually quite hard in medicine. So I don't think it's a clear picture one way or the other, but my observation from the people that I'm working with on specifically funding is a typical EDA professor maybe works, let's say, 1 month in order to get one grant. They work for a few days. Like, seems so easy to get money. That's why I'm here.
Hi, I had a quick question. Sometimes in the engineering field we use things like design of experiments to reduce the computational burden that we would have by doing Monte Carlo methods. So I just was wondering, is there something analogous that can be done in the medical field where you use design of experiments to get to a good answer faster?
Not that immediately comes to mind. I'm familiar with the field. I've applied it in my previous lives and all that. There are some places where what in EDA or what in analysis we call worst case analysis is applicable, but as a direct replacement for this dose calculation via Monte Carlo, I cannot think of something directly. I'm sure there's an application somewhere. Clearly, when you do those studies, when you do the treatment studies where maybe you take a number of patients and you apply different treatments to them to see which treatment works better, of course design of experiments is extremely important there, but in the specific area of dose calculation, not that immediately comes to mind.
You talked about the journey, and I think you summarize it here. So you talk about that a network is important, confidence is very important, and courage. And something very important you also mentioned here is humbleness. And since I know you from both your lives, you are while being very knowledgeable, you manage to keep yourself very modest. And I want you to somehow comment on it, because seems like sometimes there are some examples that the new generation think that the courage and confidence somehow should go with arrogance.
Well, thank you for your kind words, Mehdi. This is why it's great to have good friends, because they say such good things about you. I don't know if it's a cultural thing because of my background. I grew up as a very poor person in Lebanon. And in every time that I look back and see what I achieved, I think it's completely crazy that somebody was able to go from being, a young student in Lebanon to standing in front of you, telling you the things that I'm saying. I think humility is something that we all need regardless of where we are in life. In fact, no greater humility is needed than when facing the end of life. Realizing that no matter what we do, no matter what we did, what we achieved, how many lives we touched, how much money we amassed in our bank account, or how many buildings, or in the end, we're all the same. There is no difference between you and me, or Mr. Trump, or anyone like that. We're all the same. I had to say something about Trump, I'm sorry. So we're all the same. And when you realize that no one person is born more or less than another, and no one person dies more or less than one another, then we're all the same.